Hello students, in this video lecture we are going to discuss about deadlock avoidance using Banker's algorithm. In the previous video lecture I explained the basics of deadlock. What is a deadlock, what is the consequence of a deadlock, and what causes a deadlock. And in that video lecture we also had seen about the strategies. What are the different ways of handling a deadlock? And there were basically three strategies for handling a deadlock. One is deadlock prevention, deadlock avoidance, and deadlock detection. Deadlock prevention was already discussed in that video lecture itself, which was about disabling one of the necessary conditions of a deadlock. Either we can disable the or prevent the circular weight, or we may try to prevent the mutual exclusion, or we may try to prevent the no preemption. So in that way, by ruling out any one of those four conditions, deadlock could be prevented. But problem with the prevention is that it has to be done while designing a new operating system, and it cannot be incorporated into an existing operating system. And secondly, it will make the OS to be less flexible. So by eliminating one of the conditions, there will be some limitation introduced into the operating system. And especially a deadlock, given that a deadlock is a rare phenomena, making a permanent change in the operating system is not generally preferred by the designers of the OS. So it's deadlock prevention is never followed in any operating system. So deadlock avoidance is a more sensible and much more efficient technique, easier technique. So we are going to discuss about deadlock avoidance in this video lecture. So what is a deadlock avoidance? It is an alternative method for handling deadlock. So the idea behind deadlock avoidance is that you just have to make the resource allocation in a very careful manner. That's all you need to do. So the operating system, whenever the resources are requested by any process, it has to carefully assess the current situation to determine whether allocation of the resource to the process will not cause any deadlock. That is the basic idea. And for that we will be discussing an algorithm. So each process, in order for implementing deadlock avoidance, a basic requirement is that every process must declare the number of resources it's going to require during the course of its execution. So it must declare them even before it actually needs them. It just has to declare that I will be needing these resources. And as I already mentioned in the previous video lecture, you can relate this to the variable declaration required in the C programming. So unlike the C++, in C you have to declare all your variable requirements in the beginning itself. This gives a picture to the compiler how much of memory will be needed for this particular program. Same way we are going to impose this requirement in the deadlock avoidance. So based on this information we can make a plan. That plan is going to be the topic of this discussion. And the basic idea of deadlock avoidance is just to prevent the circular weight. Unlike the prevention strategy, we don't try to prevent mutual exclusion or no preemption or golden weight. We will only try to prevent the circular weight from occurring, because as we know already, circular condition is the confirmation of a deadlock. Even if other three conditions exist in the system, it still won't lead to a deadlock. Only when there is circular weight, then we have a deadlock. So this avoidance will try to eliminate only the circular weight. And what do we mean by resource allocation state is the proportion of number of available resources and the number of allocated resources. So we have the operating system has got certain number of resources, and then when processes need resources, it also makes the allocations. So at any point of time, it has the numbers of total resources and how many are currently allotted and how many are currently available. And based on this numbers, it can make a prediction whenever a request is made by a process whether it will lead to a deadlock or not. And accordingly, it will classify the system's state as safe state or unsafe. We will see what is the difference between safe state and unsafe. But basically safe state means that a state where a deadlock is not present or unlikely to occur, whereas an unsafe state is that it's either already deadlocked or a deadlock is likely to happen soon. Now what is a safe state? A state is safe if the system can allocate resources to each process in some order and still avoid a deadlock. So which means that at any point of time the resources are a total number of resources are distributed to the various processes and some resources are still available. So you have got a n number of resources. Out of that, some are already allocated to various processes and some are still in hand. They are still with the operating system, and the processes need some more resources. They will be making those requests when they need that resources. So that is the given situation. Now in that situation, if the operating system is able to verify that it can complete all the processes with the available resources, then it can be treated as a safe state. Not necessarily all the processes simultaneously. It's like the process, let's say there are 5 processes. If the operating system has got certain resources and it is able to verify that it can complete process 1 with those resources, then if process 1 is completed, it can get back all the resources allotted to process 1, and its total available resource will increase. With this increased list of resources, it may be able to complete another process. So in that way, if it is able to find some order such that it can finish all the processes one by one, then that state of the system is called as a safe state. But on the other hand, if no such sequence exists, that means that it's not able to complete one or few process in any order. So in that case, it is called as a unsafe state. So a system is in safe state only if there exists a safe sequence to complete all processes. A sequence of processes is a safe sequence for the current allocation state if for each pi the resource request that pi can still make can be satisfied by the currently available resources plus the resources held by all pj, that is those processes which are going to be completed, and their resources will be returned back to the OS, so they can also be considered as available resources. Though they are currently still with the processes, the OS can assume that if I make allocations, full allocation to all those processes, I will get back all the resources, and then it can estimate whether these resources are sufficient to complete all the pending processes. We will discuss about the actual implementation of this the safe state and unsafe calculation, so it will become clear with the when you reach that. So a safe state is free from deadlocks, whereas an unsafe state is deadlocked state. I mean, in other words, a deadlocked state is unsafe state, but not all the unsafe state are deadlocked states, because unsafe state only means that it is either a deadlock has already occurred or yet to occur, but a deadlocked state is definitely a unsafe state. So as long as the state is safe, the operating system can avoid a deadlock. So this is the basic strategy of a deadlock avoidance, that the operating system tries to keep the system in safe state. It never allows the system to get into unsafe state where it cannot complete all the processes. That is a motive. Now for the implementation of the deadlock avoidance, we need lot of data structures information. So we will discuss about these information. First one is total number of resources available. So for any system, there are some resources available. So those collection of resources and their numbers are all listed out in the resource graph, resource vector. And the next one is available. Available is resources original, I mean total number of resources are mentioned here, out of which some are already allotted to processes. Now what is available currently is this list. So available will definitely be less than or equal to the resources. It cannot be greater than that. Claim. Next important detail needed is claim. Claim is the maximum demand for each process. So I already mentioned earlier that for implementation of avoidance, a crucial information is that every process must declare in advance how many resources it's going to require during for its execution. So it may be needing different resources and different numbers, and that has to be provided here. So here each row represents the resource requirement of a particular process. So row 1 represents the resource requirement of process 1, row 2 represents the resource requirements of process 2, and so on. And each column in a row represents the resource requirement of a particular resource. For example, here C11 means that the resource requirement of P1 for R1. Similarly, C12 means the resource requirement of R2 for P1. So in that way, we can interpret the values of the claim matrix. And the next one is allocation. So claim is the maximum demand, and out of that some have been already allocated. So that allocation is what summarized in the allocation matrix, and you can now calculate the remaining pending. So once you know the claim and the allocation, and you can subtract each column value from the of the claim you can subtract the allocation value from the claim to find out how many resources are still pending for each process. This that value is also important for the algorithm, so which we can calculate manually. Now before going into a complete sample, we will take a simple sample to understand it better. So in the example, we are assuming that there is just one resource available. To keep it simple, we assume that in a given system only one resource is available, but that resource is available in 10 instances. That means there are 10 copies of that particular resource available. So 10 different requests can be simultaneously satisfied. It's like a semaphore initialized with the value 10, which means 10 resources can enter into the critical section. So that is what here also it means. So there are 10 instances of a resource available, and the max is equal to claim. So the claim is nothing but referred as max here. It is just a matter of terminology. It can we can use any term for that. So P0 needs 10 of the resource or 10 instances of the resource. P1 requires 4 instances. P2 requires 9 instances. This is the information given, the demand of each process. Now this is also an information we have got that some these resources are already allotted, which means P0 has not been allotted any resource, so it's 0, whereas P1 is allotted 1 resource and P2 is allotted 4 resources, which means 5 of the available total 10 resources are already allotted to processes, and the available resource is 5. So the question is that whether the current system is safe or unsafe. We have to determine whether the current system is safe or unsafe. For that, we need to check whether there is a sequence to execute all the process. Let us observe this. What happens if you allocate resource to P1? So what is the pending requirement of P1? 3. It's already allotted 1. So out of the maximum, 1 is allotted, and obviously the pending requirement is 3. So if you have that many resources? Yes, we have 5 resources. So that condition is satisfied. We have got adequate resource to meet the requirements of P1. So what will happen if you allocate 3 resources to P1? What will happen is that P1 will complete, because once all the resources are provided to a process, at some point of time it will complete its execution and it will return all the resources. So if P1 completes, we will get back 8 resources into the available. So the already all the resources that are allotted to P1 will be released. So the total number of resources will increase into 8. Now what will happen if you make a allocation to P2? P2's requirements are 5, and we will be having 8 resources. This is an assumption. We are not actually allocating the resources to P1 or P2. We are only assuming if I allocate the resource to P1, I will get back the resource of P1, all the resources, and with that, if I allocate the resource to P2, what will happen? So we are only making an assumption about the allocation, not actually allocating. So if we allocate the resource to P2, same thing will happen. P2 will also get all the requirements. The maximum demand of P2 will be satisfied, and it will also release all its resources. So our total number of resources will become uh, so the four resources will be are there. So with that we will be getting back all the 10 resources. The total number of resources we will be having is 10. With that 10 we can also meet the requirement of P0. So this indicates that the current state of the system is not unsafe. On the other hand, it is safe because we can complete processes in this order. We can first meet the demands of P1, then we can meet the demand of P2, and followed by P0. Similarly, we do have one more sequence. We can finish P2 first, P1 next, and P0 third. But what if you try to complete P0 first? That's shown in red color because it will lead to unsafe, because the total demand of P0 is 10, but we only have 5. So if you give this 5 resource to P0, neither P0 will complete nor other process will complete, because they all will be having demands. So none of them will complete. So this cannot be treated as a safe sequence, but only the first and second are treated as safe sequence. But to determine whether a system is safe or not, only one sequence is sufficient. That is, we can either take this one or this one. This need not be considered at all. It's just being shown here to make you understand, but this is to be ignored. So the system is currently safe. Now then the next aspect is, if P0 makes a request for resources, whether we should accept or not. For example, in the same situation, P0 requests 3 resources. Whether allocating them will lead to unsafe state or not. For that we have to do the calculation. What if we have got 5 resources currently, and out of the 5, if you allocate 3 to P0, what will happen? We will only have 2 more resources in hand, and those 2 resources are neither sufficient to finish P1 or P3, which means that that system will turn into unsafe. So the best thing we have to do is, we have to decline any request from P0. Maybe we can give 2 resources to P0 at most, because then we will have 3 resources, and 3 resources are sufficient to complete P1. So we should not give any more resources to P0. That is one, otherwise that will lead to unsafe state. This is a simple example of how to determine whether given request. So this is actually the point of running deadlock avoidance algorithm. So deadlock avoidance algorithm is triggered whenever a process requests further resources. At the time you have to evaluate the situation such that if I actually give the resources to that particular process, whether the system will continue to remain in safe state or it will get into unsafe state, just like we did now. Before going into the extended example, right now this is a this is a model sample in which we assumed that only one resource type is available, but in our original example we will see if there are many resources available, the problem will be slightly enlarged. So that is actually the original problem. But before going into that, there is also a way to do this with the help of resource allocation graph algorithm. Already we have come across the resource allocation graph. We have seen that a resource allocation graph represents the allocation of resources at a given instance, and there are 2 types of arrows: resource to process, process to resource. Resource to process means that that resource is currently held by the process, whereas process to resource means that this process is asking for or requesting for that particular resource. Now for deadlock avoidance, we are going to modify that graph by adding one more arrow type. That arrow type is called climb edge. So we have got a new edge called climb edge. The difference between climb edge and request edge is that climb edge is that this process will ask for or will request for this particular resource, but right now currently it's not demanding. This is just a submission of its requirement for future. So claim edge is about future requirement, but request edge is current. That, in other words, once the actual request is made, then the claim edge is transformed into a request edge. That is the association or relationship between request edge and the claim edge. So request edge is current demand or current request by a process about a particular resource, whereas claim edge is that it's going to request at some point of time in the future. Assignment is the same one, that is that resources are already assigned to a process. So to differentiate the request edge and claim edge, we will show them in dashed line. So we will be using a dashed line to differentiate the request edge from the claim edge. And once the claim edge is once the request is actually made, then the claim will be converted into request. Let us look at the example. So this is a graph. In this we have got four arrows. The two are already familiar to you. R1 to P1 means R1 is currently held by P1, and P2 to R1 means that P2 is in need of R1, or it has requested R1 and it is waiting for R1. And P2 to R dashed line between P2 to R2 means that as of now it's not making that request, but it will make a request for that resource at some point of time. Similarly, P1 to R2 also means the same. Now this in this case there is no cycle in any way, because these two lines are arrows are in the same direction, so there may not be any cycle. But even if there is a cycle here, it is still not a deadlock, because a dashed line is not a current request. So we should not consider this cycle involving a claim edge as a real circular void. It's only a future possibility, but by then it may P1 may have given up the resource R1, so a cycle may be removed. So a cycle involving a claim edge should not be treated as an actual circular void condition. So what we have to do is that whenever a request is actually made by, let's say, P2 for R2, this will be converted into request edge, and that request edge, if it forms a cycle, then only we have to treat it as a circular void, and we should not allocate that resource to the process. So whenever a request is made by a process for a resource, the dashed line has to be converted into a actual line, and if that actual line is likely to form a cycle, then we should not let it to happen. We must decline the resource request resource to the process and it has to make the request in future. So once a request is declined for a process, that process may remain blocked for some time, and when it is unblocked again, it will resubmit the request, and by the time the situation may have become different and it may not now form a cycle. That is the basis of resource allocation graph based deadlock avoidance. So if no cycle exists, then the allocation of the resource will leave the system in safe state, and on the other hand, if a cycle is found, then it's unsafe state. Now we are getting into the original sample, which is Banker's algorithm. It is the same one which already I explained with a simple problem. Now it's just going to be an extension with including more number of resources. It's not going to be one type of resource. There will be n type of resources involved in the problem, but the basic idea is same. So we have the available is nothing but the total resources minus already allocated resources. Max is the max is the claim matrix. So total demands of various processes, and allocation is the current allocation out of the claim or max. What are currently allocated is summarized in this particular matrix, and need is the difference between max and allocation is calculated and filled into this particular matrix. Now we are going to use the algorithm called Banker's algorithm, which is actually having two modules. The first module is called the resource request algorithm. So what happens is that whenever a process makes a request for a resource, that request will be scrutinized to check whether allocating that resource to the process will lead to a unsafe state or not. That's for that we are going to run this algorithm. So let request I be the request vector for process pi. So there is a we have already seen that there is a request vector for process pi. If resource request of j equal to k, then process pi wants k instances of resource rj. So when a request for resource is made by process pi, the following actions will be initiated. Step 1, the first thing you have to verify is that whether that request is a legal or valid request. So what do we mean by a request of a process is legal or valid is that it has submitted a claim in the beginning that I need these many resources. Now it should not exceed that particular request. So whatever the request made by the process should not exceed the claim, because claim is like the maximum requirement. So a process should only request within the claim. That is what is verified here. If request less than or equal to need I, then go to step 2. That means that it is a valid one. Whether it will be allocated or not, that is next. This condition only checks whether it makes a legal request. So if it is less than within that claim limit, then it's accepted. Otherwise, raise an error condition since the process has exceeded its maximum claim. Number 1, first condition to be checked. If this condition is satisfied, then what do you think is the next condition? The next condition is if that resource is currently available. So if a process requests for 2 instances of a particular resource, the second thing we have to check is that whether 2 instances of that resource is currently available. If that is available, then we may have to proceed. Otherwise, we have to just block the current process saying that the resources are not available. So we don't need to run Banker's algorithm for this case also, because the resources are not available at all. The third condition is that it has satisfied all the 2 conditions, that the request is a valid one and the resources are also available. Now comes the role of the Banker's algorithm. So we have the resources, whether we should allocate or not. That to determine that, we need the algorithm to be executed. So for that we have to make this arrangement that before running the algorithm, we make the temporary copy of all the arrays, because during the algorithm we will be modifying the values, and so we should not make permanent changes. It's like when you do some temporary calculation, you have to copy the values into a local or temporary variable, and then we should keep the original variable to intact. So same way we copy the okay. So what does this mean is that request of I is the current request by process I for a particular resource. Available is the total number of resources of that particular type. So we subtract a request from available, pretending like we are allocating that resource to that particular process. So after allocating that resource, the available will become available minus request. So we make a copy of that. After that, we we increase the allocation for the ith process. So because we just has allocated resource to a process, we also update the allocation vector accordingly. Similarly, the need is also adjusted as need equal to need of I equal to need of I minus request of I. So the current request that was fulfilled is subtracted from the pending need. So we have made all the changes. But in order to determine whether this allocation can be permanently done, we have to check whether it will lead to safe state or not. For that, we need the next algorithm called safety algorithm. So only if the current allocation that is just temporarily made found to be safe state, this allocation will be permanently made, otherwise it will be revoked. The system will cancel all the allocations, all the calculation it has done, and will bring back the system to its previous state. So for that, we need to determine the safeness of the situation using the safety algorithm. This is the safety algorithm. The safety algorithm uh, just has to do one thing, that it has to check whether it can find a sequence to complete all the processes. So it has to check whether I can find one process which I can complete with the resources available, and if I complete that process, I will collect all the resources of that process. Now with the increased resources, whether I can find one more process in the same way and can complete it, and if I complete that also, I will be getting some more resources. So in this way, if it is able to go and finish all the processes, then it will reply to the request algorithm that the system it will be in safe state even after the resources allocated to the process. Otherwise, it will reply with the response that avoid making that allocation because that will lead to unsafe situation. That's what is done here. So let work and finish be vectors of length m and n respectively. Initialize work equal to available. So temporarily we copy available into work. Hope you remember that available is the vector of currently available resources. So finish of I equal to false. So we assume no process has been completed as presently. Now find an index I such that finish of I equal to false. That means that it has not yet completed. At the same time, its need can be satisfied with the work. Work is nothing but available. So if you can find a process whose demand can be satisfied with what is currently available with the operating system, then mark it and collect the resources of that process into work that is available. So allocation of I is added into the available. Now we repeat this process. Try to find one more process whose finish is false and its need is less than or equal to work. So if this loop is able to go to each and every process and complete all of them, what will happen at the end of it? The need will be 0 for all the processes and the work will be equivalent to available. So the total available will be equivalent to work. That is the state where we can determine that this is a safe state. Even if you allocate the resource as requested by the process, there it will not affect the completion of all the processes. But on the other hand, if even if one or two process left out of this sequence, it means that need will not be equal to 0 and work will not be equal to available, and that is what unsafe state, and the request of the process should be declined. So this algorithm will try to complete all the process. If finish of I equal to true for all processes, if finish of I equal to true for all processes means that we are able to determine that all the processes can be completed even with the available resources after the allocation of the request. So the system is in safe state. Now we are going to take an actual problem. I think this should clear even if you have got some doubts not yet cleared. So we have got a actual claim matrix. So what you infer from this matrix is that P1 is in need 3 instances of R1, P1 needs 2 instances of R2, similarly 2 instances of R3. Similarly, all the 4 processes have different demands. This is the maximum demand of all the processes for various resources. Now allocation matrix is given as 100, means that P1 has been given 1 resources of R1 and none of the resources of other 2. So its pending request can be calculated as claim minus allocation, which is this one. So 3 minus 1, 2, 2 minus 0, 0, 2 and 2 minus 0, 2. So in this way we calculate the C minus A and keep it here, and the resource vector is given as 936, and from the with the help of the allocation we can easily calculate the available. This is not given in the problem, but it was calculated with the help of the allocation. So resource minus allocation is what available. So we can calculate the available in this way. Now the question is that what if P2 makes a request for one additional unit of R3, whether allocation of that resource to R3, I mean that to P2, will result in safe state or unsafe state. We have to determine using the algorithm. So what is the first step? The first step is you have to check whether this request made by P2 is valid or legal. So we have to check it here. So what is the resource requested by P2? R3. R3's claim is for P1 is 2, and it has not been allocated any resource so far. So one resource for R3 by P2. Okay, I think I looked at P1. So actually we should look at P2. So for P2, its demand of R3 is 3 and it's allocated 2 resources already. So making one more additional request for R3 is valid only. So it has passed the first test. The second is, do we have R3 available? We have to look at into the available vector, and we can see R3 is available in exactly one quantity. So that is also verified. Now the role of the Banker's algorithm or the safety algorithm. So we have to check, after allocating this resource to P2, will it be safe state or unsafe state? So we are going to determine that. So we assume that the resource is allocated to R3, which means that this value becomes 3 and available becomes 0 for R3. Now we have to identify any one process that can be completed with 0, 1, 0. So with the one resource of R2, can we complete any one process? Let us check whether we have got two processes which need one resource of R2, but they also need other resources, so we can't complete them. Since P2 has met its resource requirement, it eventually completes. Yeah, we missed one thing, that P2 has already been fulfilled with the total demands. So its original request is 613. We have already made the allocation for P2. What will happen as a result of this is that it will release all the resources to the operating system, which means the available will increase 6 plus 0, 1 plus 1, 3 plus 0, which means it will become 6 to 3. Now with the 6 to 3, can we complete any other process? So we can easily complete, I think we can complete P1. So P1 can be allocated all its resources with the available. So we allocate the resources to P1, and once again P1 will also release all its resources, which will result in the allocation, the available further increasing to 7 to 3. And we just mark that two process can be completed. Now we need to complete another process. So the next process is P3. P3 can also be allocated and completed. So P3 is also completed, and we get back all the resources of P3 also. So it becomes 934. Now obviously finally P2 may be allocated 1 unit of R3 and it's requesting without violating. So once we complete all the 3, P4 can also be completed. Now what is the final conclusion is that this request of P2 can be accepted. It is for that determining that particular one, we did the entire algorithm, we executed the algorithm that P2 can be allocated one unit of R3 safely, since we are able to find a sequence of completing all the processes. So this is the steps we followed. We tried to we assumed that we allocate the resource to P2 and updated the available accordingly, and then we tried to find one by one processes that can be completed using the available resources, and we are able to finish all the processes, and so we can give a reply to the safety algorithm can send a return value to the resource allocation algorithm, saying that you can go ahead with the allocation of the resource to P2, since it's not going to violate the safety state. So this similarly, this is one more example that in this example P1 requests one unit of R1 as well as R3, but the procedure is same. We have to check whether the request is valid, then we have to check whether the resources are available, and then we have to make an assumption that if we allocate the resources of resource R1 and R3 to P1, what will be the available after that, and with that available we can find one process to complete, and if that is completed we increment the available by adding the resources of that particular process. So in this way we must go on to finish all the processes. So this is the basic idea of Banker's algorithm. So Banker's algorithm will be like this. So you will be given an allocation matrix or claim matrix and available. So these three are basic requirement. We can't manipulate it. The problem has to be providing these three details: the claim matrix or maximum matrix, allocation, and available. With that we can calculate all the remaining. That is, we can calculate the total resources from available. It is nothing but the sum of allocation and available will tell you the maximum resources available in the system, and we can also calculate the pending requirement by subtracting allocation from max, and we can then run the Banker's algorithm. So we can claim that the system is currently safe state indeed, because the sequence P1, P3, P4, P2, P0 exist that satisfies the safety condition that we can finish all the processes with the available resources. So the first response is that currently the system is safe. Suppose that the process P1 requests one additional instances of A and two instances of C, which means the request submitted by P1 will be 102, 1 of R1, 0 of R2 and 2 of R3. To decide whether this request can be granted or not, we have to check whether it's less than or equal to available. That is whether we have the resources. If that is true, then we make that allocation and run the safety algorithm to determine whether this allocation has not affected the safe state of the system, just like we did in the previous example. So deadlock avoidance summary. The advantage of deadlock avoidance is that we don't have to make permanent change in the operating system. We just have to add an algorithm into the operating system. So we can implement it in any operating system which don't have the mechanism of deadlock handling. It can be just added by running this algorithm. Whenever a whenever a resource request is made by a process, instead of immediately allocating the resource, we just have to assess the allocation using the Banker's algorithm, whether it will lead to deadlock or not, whether it will cause say unsafe state or not. So we can implement it in any OS. That is the main advantage of deadlock avoidance. and it will never allow a deadlock to happen. As long as we are strictly following deadlock avoidance algorithm for every resource allocation, a deadlock will never occur. As a result, we never have to deal with the deadlock. Deadlock is always prevented, so we don't need to do anything about the deadlock handling. Next is limitations. Maximum resource requirement must be stated by every process, which is not always possible. Some resource requirements may suddenly arise at runtime, so that cannot be submitted in the beginning. And processes under consideration must be independent. No synchronization requirements should be there. There must be a fixed number of resources to allocate, and no process may exit while holding the resources. These are all limitations. In addition to that, there is one more limitation, is that it will become very slow process, because for every resource allocation you have to run an algorithm, which is a CPU intensive task. So you have to it's more like a context switching. So context switching consumes a lot of CPU time, as it's a overhead. The same way, the banker's algorithm will also become a overhead. So, and that's why I said in the during the previous video lecture that uh, most of the operating systems simply follow the fourth strategy for deadlock handling, which is simply ignoring the problem. It is because of this overheads that it has to implement the algorithm, and it has to construct all the vectors and matrices to implement the banker's deadlock avoidance. So next video lecture we will discuss about the last strategy of deadlock handling, which is deadlock detection. Thank you.